Alright, so in this video, we're going to do an introduction to Bayes' theorem. And really what we're going to be interested in doing with Bayes' theorem is just attacking conditional probabilities from a different method, from a different direction, I should say. That's what Bayes' theorem has to do with, or what Bayes' theorem deals with, I should say. Alright, so let's motivate Bayes' theorem a little bit before we actually talk about the theorem, and then do another example, and then we will do more examples in class, as usual. So let's say that there's a rare medical condition and only 0.1% of the population actually has this condition. Suppose further that we have a test for this condition, that if you have the condition, then you get a positive result 97% of the time you take the test. If you don't have the condition, then you get a negative result 99.5% of the time. So the question is suppose you get a negative test from the doctor. Does that mean you should really be worried about it? Or should you ask for a second test? All right. So really we're looking at a conditional probability. Given that you test positive, what's the probability that you actually have this medical condition? So let's let A be that you have the condition, and let B be the event tests positive. So then we want to figure out the probability of A given B. We already have the conditional probability formula, where we do the probability of the intersection over the probability of the given event. So in this case, probability of A intersect B over the probability of B. But notice that we don't have either of these values given to us explicitly, right? We don't know what's the probability that you test positive. I know the probability of having the condition, but I don't know the probability of that we test positive. Okay. And likewise, I don't have it that you have the condition and test positive. I don't have that information. All right. So what we're going to do is we're going to rewrite the numerator and the denominator in terms of what we are given. So let's just write down what we're given. We know that the probability that you actually have the condition is 0.001, and which means that the probability that you don't have the condition is 0.999. Now we also have some conditional probabilities. We know that if you can have the condition, we know how accurate the tests are, whether or not you have the condition, I should say. So if you have the condition, then we know that the test was 97% accurate. So given, if you have the condition, the probability that you test positive is 0.97. Likewise, we would know that if you have the condition and don't test positive or test negative, then it would be 0.03. We know that conditional probability too. This is an either or situation, so these would have to add up to 1. Likewise, we know that the test is 99.5% accurate when you don't have the condition. So if you don't have the condition, the probability that you don't test positive is not 0.995. So that means that if you don't have the condition, the probability that you test positive is 0.005. And again, these two are either or situations, so they have to add up to 1. All right, the numerator was an intersection. Going back to the conditional probability formula, that numerator was an intersection. So using our conditional probability, we can rewrite that intersection using A as the given event rather than B. The reason why we're using A as the given event is because I know something about the probability of A up here. So I can rewrite the intersection in this fashion. I know the probability of A. I also know the probability of B given A. So now I can figure out what the numerator is. Great. Let's think about the denominator. The denominator was probability of B. Well, looking up at what we're given, I know information about B in terms of A and in terms of A complement. Notice I have that information here, and I have that information here. And I also know the probabilities of those pieces, the probability of A and the probability of A complement. So let's rewrite, we've done this before in other examples, let's rewrite B in terms of elements that are in B and A at the same time, elements that are in B and A complement at the same time. Remember, A and A complement are either ors, right? So if you're an element of B, you're in A or you're not in A. and there's no overlap. So those two things are mutually exclusive. So I can break the probability up over that over the union as a sum. Cool. Now I've got probabilities of intersections, which means we can rewrite those in terms of the conditional probability formula. So our denominator here becomes, we're going to use the A and the A complement as the given event because we know something about probability of A and probability of A complement. So we write probability of B is probability of A times probability of B given A, and then plus probability of A complement times the probability of B given A complement. And like I mentioned before, it's just like the numerator, we know each of these values. All right, let's put everything together. We've got the probability of A given B is equal to the probability of the intersection of A and B, which we're replacing with this expression that we just talked about a little bit ago, and over the probability of B, which we're now replacing with this expression. Now we have all these pieces. Probability of A, 0.001. Probability of B given A, 0.97. Same expression here in that first part of our denominator. Second part, probability that you do not have the condition is 9.999. Probability of a false positive, that's what this is, right? You do not have the condition, but you tested positive, 0.005. Remember, the test was accurate 99.5% of the time if you don't have the condition. Simplify that, you get 0.1627. So even though you've got a test that's 97% accurate for positives, there's still only a 16% chance that you tested positive, given that you tested positive, that you still have the disease, that you do have the condition. So it's much, much more likely that this is a false positive than you have the condition. So you would ask the doctor to run the test again. Now, if it comes up positive twice, then you probably do have the condition. All right, so this leads us into Bayes' theorem. That's a very specific example of Bayes' theorem. So this leads us into Bayes' theorem, so let's talk about that. So first part says, suppose you can break your sample space up into a disjoint union of n different events. In that previous example, we did it with a disjoint union of 2 events. In this, we're just generalizing that idea to more than 2 events. Well, just like before, then since the A1 through AN take up your entire sample space and are disjoint, we can write B as a disjoint union of B's intersection with each of those events that make up the sample space. In the previous example, it was B with A and B with A complement. Here it's just, if an element's in B, it has to be in one and only one of these A sub i's. So now let's work with the conditional probability formula to figure out what Bayes' theorem actually says. This is just our statement of conditional probability. This is just a rewriting like we did in the previous example. So here, this is just rewriting the probability of the intersection as the A sub n is the given information rather than the B. And then down here, this is just a statement of the probability of B. We have B as a disjoint union. So if we take the probability, we can break it up as a sum. That's where the plus signs are coming from. And then we're writing each of the intersections as a conditional with the A sub I as the given information. Okay, so that's all this is, and this looks a lot like what we just did in the previous example, just as a general case. All right, so let's do a specific example with this. Let's say we have a hospital emergency room. Patients are classified as critical, serious, stable. In this case, 20% are critical, 30% are serious, 50% are stable. So notice that that's our sample space. We've taken up all 100% of the patients. Now we've got some conditional probabilities given to us. For the critical ones, 30% die. Serious ones, 10% die. Stable, 1% die. So given a patient dies, let's find the probability they started out being critical. Okay, so notice that we have information about dying given critical, but we want critical given dying. It's the wrong direction. So what Bayes' theorem does, notice up here in the problem, it basically flips around our conditional, right? I have, just like what I said specific to this example, I have information of given critical, what's the probability they die? Given serious, what's the probability they die? I'm given the conditional in the reverse order, right? So we use Bayes' theorem to flip the order. So here's our probability of the condition, or the conditional probability of C given D. Now flip things around. Make C the given information, right? Make C the given information, and then work with the probability of D. Well, D can be broken up into three cases in this case. Your die and your critical, you die and your serious, you die and your stable. So let's break up die into those three categories, and then make the pieces given that we know. We know die given critical, die given serious, die given stable. So we break up all those intersections in that way. One thing to notice is whatever you have on top is going to be a piece at the bottom, by the way. This always happens. Okay. Now we know all of these pieces. Probability of critical was 0.2. Probability of death given critical was 0.3. Likewise, probability of serious is 0.3. Probability of death given serious is 0.1. Probability of stable is 0.5. Death given stable is 0.01. And we get about 0.632. So if the patient died, it was a 63% chance they were classified as critical to start with anyway. We'll do more of these Bayes theorem problems, but again, like I mentioned just a minute ago, the whole point of this is that you're trying to flip the conditional around into conditional probabilities that you were given information for. In this case, we were given something about if it was critical, then what's the probability they died. So the given information was critical, given information was serious, and so on. We wanted to flip it. We wanted the flip, right? We wanted the given death, and we didn't have that. So that's why we used Bayes' theorem to help switch it around.